Hi, this is Baifeng Shi from UC Berkeley. This is joint work with Trevor Darrow and Xin Wang. This work studies top-down attention, which is a concept opposite to bottom-up attention. So bottom-up attention means attention that is only dependent on the input. It will normally highlight all the salient objects in the image. And on the other hand, top-down attention means attention that is directed by the high-level task. It only highlights the object that is relevant to the task while ignoring the others. And this can help us extract a task-adaptive representation. However, we find that current top-down attention algorithms do not have a principal design, and they are not compatible to the vision transformers. So motivated by this, we propose APS-VIT, a VIT-based model that has the ability of top-down attention. We show that APS-VIT is able to adjust its attention to different objects given different tasks. And we also find APS-VIT is able to improve performance on vision language tasks and vision-only tasks. Okay, so now let's dive into some details. Our design of APS-VIT comes from this classic idea called analysis by synthesis, or ABS. Basically, ABS hypothesized that our vision perception is a Bayesian inference process, which means our perception of an image does not only depend on the image itself, but also depends on a high-level prior about the image. And in this work, we find that top-down attention could be a natural consequence of Bayesian inference. So the intuition is that we can formulate the high-level task as a Bayesian prior, which will affect the latent representation and attention. So we don't show any math details here, so please refer to our paper. But anyway, our conclusion is if we can train a model to learn Bayesian inference, it learns top-down attention as well. So with this inspiration, we propose analysis by synthesis vision transformer, or APS-VIT. So APS-VIT is a VIT-based model which learns top-down attention by approximating Bayesian inference. So let's first look at the architecture of APS-VIT. So basically, APS-VIT is a VIT with a feedback loop. And APS-VIT processes an image with 4 steps. So step 1, we pass the image through the feed-forward path, which is just a regular VIT. And in this step, the attention is bottom-up, so it normally focuses on all the salient objects in the image. And in step 2, after we get output tokens from the feed-forward path, we embed the current task as a vector and use this task embedding to reweight the output tokens from the first step. And a token will get higher weights if it is more relevant to the current task. So this step coarsely selects which tokens are relevant to the task. And step 3, we send back these reweighted tokens through the feedback path and into each self-attention layer. Note that the feedback path here only contains linear layers. And in step 4, we run the feed-forward path again, but this time each self-attention layer will receive an additional top-down input. And we add the top-down input to the bottom-up input for the value matrix in self-attention. And in this way, we will signify the task-relevant features in each layer. And so how does APS-VIT learn this top-down attention? So as we mentioned, it can learn top-down attention by approximating Bayesian inference. And here we optimize a vibrational loss to achieve that, which is quite similar to the VAE loss. So basically, there are 2 parts of the loss. The first one is the alignment loss, which means that we want the final output to be aligned with the task embedding. And the second one is reconstruction loss, which means we want the feedback path to reconstruct the input image from the output tokens. And by optimizing these 2 losses, and along with any regular supervised or unsupervised loss for the task, the model can learn top-down attention. So to see if APS-VIT truly learns top-down attention, we did an experiment where we randomly sample 2 images from ImageNet, and we used the class embedding of each class as the prior, and then we observed that the model is actually able to adjust its attention to different objects when given different priors, and the model will actually give corresponding different classification results. And for the experiments, we apply apps VIT on visual language tasks such as VQA and still shot image retrieval, and we use language to guide the visual attention. So it turns out apps VIT is able to focus its attention on the objects that is relevant to the language input. And we also show that apps VIT is able to improve the performance on both tasks. We also apply apps VIT to vision-only tasks, such as image classification and semantic segmentation. So in these tasks, we use a learnable task embedding to guide the attention. And it turns out apps VIT is also able to improve performance on these tasks, and it can also improve the robustness of the model against noisy or out of distribution images. And by visualizing the tension maps, we find that the tension of apps VIT is actually cleaner and it is more focused on the foreground objects. So thank you for listening. If you are interested, please visit our webpage, GitHub, or archive. Thank you.